This is project 6, video 1, the pencil and paper part. So we got a train moving along a track beside a person. Starts out 500 meters away from the closest point of approach and winds up 500 meters away in the opposite direction. So travels a total distance of 1,000 meters. I think the first thing I want to do is to get the time. So I'm going to say delta x is equal to v delta t. I want to find out how long it takes to go from 500 meters away in one direction to 500 meters away in the other direction. Delta x is 1,000 meters, so delta t is going to be equal to delta x divided by v. Alright, then I imagine a lin space of delta t values, and I gotta calculate, create 100 delta t values, and then for each one, gotta find out where it is. So I need to establish a coordinate system. Hopefully people do it on their own, so different people establish different coordinate systems. I'm going to choose, I really only need an x, but I'll call it an xy coordinate system. I guess the person is somewhere at a non-zero value of y. But I'll put the person down here. So this is where the receiver is. At a distance, we'll call it d from the track. And then I'll have the train moving along the x-axis, so the track extends along the x-axis, and this will be plus 500 meters to minus 500 meters. So at some instant in time, the train will be here, for instance, traveling in this direction. V sub t for the velocity of the train. Might be better to call that v sub s for the velocity of the source, but I think I'll use v sub t. So I have 2 v sub s, and my Doppler effect equation will be substituted by v sub t. So here's a line extending from the train whistle to the person, and I need a couple of things. For any given time, I need to know where the train is, any given time between time 0 and time delta t, where the train is. So the velocity of the train is in, the x component of the velocity of the train is negative. So I'm going to go the position of the train is x0 plus v0x t plus 1/2 at squared. The acceleration is 0, so it's just this. So x is equal to 500 meters so I'm going to go, let's see, delta x, let's keep track of some variables here. Delta x is equal to 1,000 meters. x0 is equal to 500. Not variables are really constants. 500 meters. So minus v sub train times t. So a skinny eraser there. Get a minus sign. Alright, so that's the position of the train. After a while, with that being 500, if we wait long enough, it's going to start having negative values when it's over here, all the way to minus 500. Okay, so that's good. Now I need the component of the train along this vector along this line from train to person. So I need a little vector component diagram. I think I'll try drawing that down here. Let's see. I think I better get a little more space here. Alrighty. So I need the component of the velocity in the toward the person direction. The component of the velocity of the train in the toward the person direction. Alright. At a time when the train, whatever that time is, when the train between 0 and delta t is at position x. So in my diagram, I've got this green line. I'll make it green here too. So in some sense, that's my set of coordinate directions, one that way, and the velocity of the train, I had it in red up here, vt. Is VTP, the velocity toward the person, and VTP is equal to VT times the cosine of theta. So I got a theta I've defined. This distance is x. I think I want to mark that off up here. Yeah, just call that x from there to there. And so this, by Pythagorean theorem, the distance from the person to the train. Remember, x is the distance from, well, it's actually the position variable, but well, it's to the right there. It's also the distance from the point on the track closest to the person to the position of the train. So this will be, by Pythagorean's theorem, the square root of x squared plus d squared. So cosine of theta is just x over square root of x squared plus d squared. So this is equal to the velocity of the train toward the person is the speed of the train. That's given by the user. That's one of our arguments. I forget whether it's the first or second argument. Takes two arguments. The first argument being the distance. So d, what I call d, is the first argument, and then the second argument being the speed of the train. So vt is the speed of the train. It's the second argument. The speed of the train component toward the person, the velocity, the component of the velocity toward the person is the speed of the train times x over the square root of x squared plus d squared. Alright, that's what we need for our Doppler effect formula. Copying that off the formula sheet. We have, well, let me copy it directly. Normally I would skip this step, and you can too, but V plus minus VR all divided by V minus or plus VS and then times the original frequency. So this is the received frequency. All we have moving is the source. And what I've got is the component of the velocity toward the person. So toward the person makes it higher, so I got to choose the minus sign. So f prime is equal to, oh, and VR is 0, so I can ignore that part. V minus VTP. Well, I guess, yeah. I think well, let's go, just to make sure I got pure substitution. So then f prime equals V minus VTP, the component of the velocity toward the person, times the original frequency. Alright. So, this is, I think I'm pretty much there. So I got the velocity of the train toward the person expressed right there. And I got the frequency. Let's, we do have to worry about, after a while, this is good at least up until the origin of my coordinate system. And after that, the component of the velocity, if I look at a position over here, when the train is over here, if I break that up into components, the velocity of the train. So I'm letting this diagram serve double duty, but I'll try to use all. It would be the same kind of thing, same kind of diagram that we had for a vector component diagram here, but this is theta, which would be the magnitude of x, or the cosine of theta would be the magnitude of x over this distance, so the formula would be the same, except I got to worry about the algebraic sign. But the thing is, this velocity, the component of it along that line is actually going to be away from the person. So if I just use whatever the value of x is, that builds that minus sign into the cosine of theta already. And other than the magnitude is the same, it's just that it's supposed to turn out to be the negative of it. So let me look down here. So it'd be the negative of the velocity of the train times the cosine of this angle, if x itself is negative. And that's really just what I want, because the component of the velocity along that line is away from the person. So I'm using a minus toward to represent away. And so it would be just as before for the same angle, but with a minus sign. And then if I actually stuck that VTP in there with a minus sign, then it would be plus the magnitude of it. And that would make the denominator bigger, which would make f prime lower, which is exactly what we want when it's moving away. So this formula, our whole method, get a value for VTP and stick it into here to find out what the frequency is going to be good for any time, for any position along the track there. With my coordinate system. So let's try to create an outline of the steps. So find delta x. So one outline. So this is called writing pseudocode, is what we're doing, writing pseudocode. One, initialize. all I can think of is delta x and x0. Delta x equals 1,000 meters, and x0 is equal to 500 meters. Okay, that was step 1. 2, I'll leave extra room there in case I have to initialize other stuff that I haven't thought of yet. 2, calculate length of time interval. And rather than referring to an equation, I think it's just as fast to write it down. It's delta t is delta x over v. X over Vt, the speed of the train, which is given by the user. And I should add that subscript. It's a constant speed of the train. I'm calling it V sub t. Didn't like that last one. V sub. Looked too much like a plus sign. Okay. Then calculate. Create a time array. I'll call it times equal linspace 0 to delta t. I'll try it with 100, but if the curves don't look smooth, then I'll create more. And I think for here, just to cut down on writing, I'll just call that t. So I might call it times in the program to emphasize that it's an array of times rather than just one time. But I think it would be okay to call it t. We'll see when I get there. But to make it so I'm more or less just copying these formulas, I want to use t. So then create an array of positions. Positions using x is equal to x0 minus vt times t. It's an array because t is an array. So create array of positions using that. And then at each position, calculate VTP, the velocity of the train toward the person, using this formula. Toward person velocity components. So create an array of toward person velocity components using, I'll just put a colon there, VTP is equal to, I think it was VT times the cosine, which is x over square root of x squared plus d squared. Now x is an array, so I got to use the x dot to the power of 2 and the dot slash instead of just the regular symbols, because I am working with an array. Alright. Then I think I'm almost there. Yeah. Then evaluate, create an array of frequencies. Create array of received frequencies using f prime equals, I think it's v divided by v minus vtp times f, and f itself is one of the givens. Check to make sure I got that typed in right, because I think, that I wrote that down right. There it is, right there. And f was one of the givens. No, it was given in the problem, but I have to initialize that. So let's include that here. F equals 440 hertz. Alright, so then plot I want the frequency versus the time, so I go t comma f. Alright, that should do it. Keep in mind, I sometimes make mistakes while I'm doing the pencil and paper, so you know, if I were doing it, I would want to finish up the whole project in time to turn it in at the start of class, because sometimes when I'm coding it up, that helps me correct any errors that I might find in the pencil and paper part. So, but I think I've got it. So that'll be interesting. Oh, they did say do the special case, so I gotta create a test case. I guess I can probably put that up here. Let's see where I got room. So I'm going to try to create a test case right here. So test case. So if it's a fictitious test case because the person is 0 meters away from the track, that means they're right on the track, which wouldn't work. They'd get hit by the train. So but we pretend we got some indestructible receiver at the same elevation as the whistle, right on the train, so 0 meters away, and see what it would look like. So in that case, the train's always coming directly toward the person. It's not going to check everything. It's clearly not going to check my angles, but if I got that picture in mind, then the other cases I should be able to see if they look right. So it's a useful test case to some extent, and it's an easy one. So it's a mix of being easy and still somewhat useful that made it so I picked that one for you. But the 50 meters per second for the train was arbitrary. So before it passes you, it's coming right at you. Receiver on track. So before passing person. F prime equals V over V minus VTP, which is just going to be 343. Oh, there we go. Didn't put that in there either. So as far as initializing stuff, I gotta initialize the V equals 343 meters per second. Okay, so test case help remind me of that. 343 meters per second divided by 343 meters per second minus, and V toward is just 50 meters per second. And then go ahead and evaluate that. No, I'm not quite ready to evaluate it. Let's fix this formula out. Times the original frequency, and so that would be times 440 hertz. And now I'll evaluate it. I get 515.1 hertz. I'm going to be checking it against a graph, I think, so I'll just call it 515 hertz. And after passing person, V toward the person is going to be equal to a minus 50 meters per second. So we'll have same thing as before, F prime equals V over V minus VTP times F. And this time it's equal to 343 meters per second divided by 343 meters per second minus a minus 50 meters per second, all times 440 hertz. And that evaluates to 384 hertz. So for that case, the graph would just look like this would be frequency versus time, and the graph would be up here at 515 from time 0 up to time delta t, and then that'd be 515 hertz. And it dropped down to 384 hertz. And I got a false 0 in there. I guess I don't really like that. So it's not wrong. It just makes it a little confusing for the reader. So yeah, let's put that down about there. Time. Might want to worry about that. I'll see how that looks. We might wind up having an intentional false 0 on the graph, but it'll just be at a high frequency and then suddenly drop to the lower frequency. That would be the instant when it passes the person. Remember, the person, the fictitious person in this case, is right on the track. So it starts out at 515 hertz, and it's a steady 515 hertz because the train's coming directly at the person, and then boom, it switches to 384 hertz if I've done these calculations correctly. Okay, So now I got the check case taken care of, and I might, if I have to fix something up, it'll be while I'm programming, or maybe even while I'm going through the checklist. Make sure I took care of everything, including here, but I think I got it covered for this video. So thus ends Project 6 video number 1.